Hello dear students, let us solve some numerical problems related to organ pipes and staged strings. At first let us review the related formulas. In closed organ pipes, nodes are formed at the closed end and antinodes are formed at the open end. Therefore, the fundamental wavelength corresponds to 4 times the length of tube, that is lambda by 4 is equal to L. And in case of open end pipe, both open ends are at antinodes, therefore fundamental frequency corresponds to half wavelength as shown in this. Same is the case in case of staged string, where the nodes are formed at the fixed ends and the fundamental frequency corresponds to lambda by 2 is equal to length L. First formula, for closed organ pipe, fundamental frequency F1 is equal to B upon 4 L, where B is the velocity of sound in air and L is its length, which is B upon lambda 1. And F2 is equal to 3 F1 frequency, which is frequency of second mode or first overtone or third harmonic. Similarly, F3 is equal to 5 F1 and so on. For open organ pipe, F1 is equal to B upon 2L, which is B upon lambda 1. F2 is equal to 2 F1, F3 is equal to 3 F1 and so on. So, in case of open organ pipe, both the even and odd harmonics are present. For resonance tube, velocity of sound in air at lab temperature is equal to 2F L2 minus L1, where L1 is length of air column for first resonance and L2 is length of air column for second resonance. F is frequency of the tuning fork used. Second, end correction for resonance tube is equal to L2 minus 3L1 upon 2, which is denoted by symbol C. For staged string, velocity of transverse wave in the staged string, B is equal to under root T by M. Fundamental frequency F1 is equal to 1 upon 2L under root T by M, which may be written as 1 upon 2L. T is equal to weight, that is W into G, and small m is mass per unit length, which is pi r square into rho. 1 upon L d under root W into G upon pi into rho, where r has been replaced by d by 2. So, d square by 4 under root 4 here cancels this 2. Thus, we see that frequency is inversely proportional to the diameter of string. First question is, one day when the velocity of sound in air is 340 meter per second, the fundamental frequency of a closed organ pipe is 220 Hz. How long is the pipe? Second, the second overtone of the pipe has same wavelength as third harmonic of an open pipe. How long is the open pipe? Solution. Yeah. Given B is equal to 340 meter per second, which is velocity of sound in air. F1 for closed pipe is equal to 220 Hz. This is fundamental frequency for closed pipe. We have to find the length of closed pipe. In second part A, and this is part B. In part B, if wavelength of second harmonic, second overtone of closed pipe is equal to wavelength of third harmonic of open pipe, then length of open pipe is what? Solution. In A, fundamental frequency for closed pipe is given by V upon 4 L of closed pipe, which gives L of closed pipe as V upon 4 F1. So L of closed pipe will be 340 divided by 4 into 220, which gives 0.386 meter. In part B, according to question, wavelength of second overtone of closed pipe means lambda. Second overtone means F3. So, lambda 3 of closed pipe is equal to third harmonic means lambda 3 of open pipe. Now F3 of closed pipe is equal to 5 F1, that is 5 into 220, which gives 1100 Hertz. Therefore, lambda 3 of closed will be equal to V upon F3 closed, which gives 340 upon F3 means 1100, which gives 0.309 meter. 0.309 meter. Now, for open pipe, lambda 3 open will be equal to lambda 3 closed, which has been calculated at 0.309 meter. Therefore, L of open pipe will be equal to 3 lambda 3 by 2, which is 3 by 2 into 0.309, which gives 0.46 meter. Question number 2. A wire of mass per unit length 10 to minus 3 kg per meter is staged by a load of 4 kg over the two bridges of a sonometer wire 1 meter apart. It is struck at the middle point. What would be the wavelength and frequency of its fundamental vibration? Solution. Given for sonometer wire, length between two bridges is 1 meter. Mass per unit length is 10 to minus 3 kg per meter. Load is 4 kg. We have to find fundamental frequency and corresponding wavelength. When the wire is struck at the middle point means like this, struck here, then clearly L will be equal to lambda 1 by 2. Solution. First, F1 will be equal to 1 upon 2L under root T by M, which is 1 upon 2L under root T means W into G upon M. Values are known. 1 upon 2 into 1 and 2. W is 4 and G is 10. M 10 to minus 3. We get F1 as 100. And second part, here L is equal to lambda 1 by 2 in fundamental mode. Therefore, lambda 1 will be equal to 2L, which is 2 into 1 is equal to 2 meter. Question number 3. A steel wire of length 20 cm and mass 5 gram is under tension of 500 Newton and is tied at both ends. Find fundamental frequency. Solution to question 3. Mass per unit length will be, mass is 5 gram, 0.005 kilogram, and length is 20 cm is 0.2 meter. So we get mass per unit length as 0.025 kg per meter. Therefore, the fundamental frequency will be, here tension is 500 Newton. Therefore, fundamental frequency will be 1 upon 2L under root T by M. 1 upon 2, L is 20, cm means 0.2 under root T 500, small m is 0.025, 353.55 Hertz. Next question number 4. A piano forte wire having a diameter of 0.9 millimeter is replaced by another wire of diameter 0.93 millimeter. If the tension is as before, what is the percentage change in fundamental frequency? Solution to question 4. Given for piano wire, that is stage distinct, other things remaining same, diameter is changed. So percentage change in fundamental frequency is what? When wire of diameter d1 is equal to 0.9 mm is replaced by other wire. Other wire of diameter d2 is equal to 0.93 millimeter. Here density and tension are remaining same. So density and tension are same. We know fundamental frequency is inversely proportional to diameter. Therefore, F upon F dash will be equal to D dash upon D, that is D2 upon D1, D2 upon D1, D2 is 0.93 millimeter and D1 is 0.9 millimeter. Millimeter cancels out. 0.967 F. Therefore, percentage change will be equal to F dash minus F upon F into 100, that is 0.967 F minus F upon F into 100. F cancels out and we get minus 3.3%. Minus indicates that the fundamental frequency is decreasing. So, is equal to 3.3%. Neglecting negative sign. Question number 5. A wire tied down between 2 points 80 cm apart has mass 40 gram. The wire vibrates in fundamental mode with frequency 60 Hz. Find the speed of transverse vibration in staged wire and the tension in the string. Solution to question 5. Given length of wire is 80 cm meter. Mass of wire is 40 gram, 0.040 kilogram. Therefore, mass per unit length will be 0.040 upon 0.8 kg per meter, which gives 0.05 kg per meter. Fundamental frequency F1 is 60 Hz. We have to find speed of transverse wave. In the string and tension in the string. T is what we know. First, we know that fundamental frequency of stage distinct is given by F1 is equal to 1 upon 2L under root T by M, where T by M is equal to small v. So we can write it as 1 upon 2L into small v, velocity of transverse vibration, which gives v as 2L F1, 2L is 0.8 and F1 is 60. Velocity comes to be 96 meter per second. Second part, v is equal to under root T by M, which gives v square is equal to T by M, and therefore T will be equal to M v square. M is 0.05, v is 96 square, which gives tension as 460.8 Newton. Now question number 6. A cord of length 1.5 meter is fixed at 2 ends. Its mass per unit length is 1.2 gram per meter and the tension is 12 Newton. What is the fundamental frequency? Second, what tension is required if n is equal to third mode has frequency 0.5 kilohertz? Solution given for stage distinct L is equal to 1.5 meter, mass per unit length is 1.2 gram per meter, that is 1.2 into 10 to minus 3 kilogram per meter. Tension is 12 Newton. We have to find fundamental frequency, first part. In second part, if F3 is equal to 0.5 kilohertz, means 0.5 into 1000 hertz, that is 500 hertz, then what tension is required? Second part. Now solution. First part, F1 will be equal to 1 upon 2L under root T by M, values are known, 1 upon 2 into L is 1.5, tension is 12 and M is 1.2 into 10 to minus 3. This gives a frequency as 33.33 hertz. First part. Now second part B, F3 will be equal to 1 upon 2L under root T dash by M. We have to find tension T dash, therefore squaring both sides we get F3 square into 2L square will be equal to T dash by M. Therefore T dash will be equal to M. This can be written as F3 into 2L whole square. Values are known. M is 1.2 into 10 to minus 3. F3 is 500 into 2 into L is 1.5 whole square. This gives a tension as 300 Newton. Next in question number 7. For resonance tube, length of air column for first resonance is 17 cm. Length of air column for second resonance is 52.6 cm, and frequency of tuning fork is 512 Hz at 27 degrees Celsius means 300 Kelvin. We have to find the velocity of sound at 0 degrees Celsius and end correction of the tube. Question. Solution to question 7. Given for resonance tube, experiment. L1 is 17 cm, length of air column for first resonance. Similarly, L2 is 52.6 cm, length of air column for second resonance. Resonance. Frequency of tuning fork is 512 Hz. Temperature is 300 Kelvin. First we have to find V0. Now velocity of sound at lab temperature in air at lab temperature is B is equal to 2F L2 minus L1, 2 into 512 into 52.6 minus 17. This gives velocity as 36,544 cm per second, means 36,544 cm per second. When divided by 100, it gives 365.44 meter per second. Now we know V upon V naught will be equal to T upon T naught. This gives V naught as V T naught upon T, values are known, 365.44, and to T naught means 273 Kelvin upon T 300. On simplification we get V naught as 347.75 meter per second. This is velocity of sound in air at 0 degrees Celsius. Second part. End correction. C is equal to L2 minus 3 L1 upon 2. L2 is 52.6 minus 3 into 17 by 2. This gives C as 0.8 cm, which may be written as 0.008 meter. Next question number 8. An open pipe 30 cm long and a closed pipe 22 cm long, both of the same diameter. Each sounds are in same diameter and each sounds in first overtone. If they are in resonance, find their end correction. So, solution to question 8. Here, this is closed organ pipe, 30 L of C is equal to 23 cm. This is open argon pipe. L of open is 30 cm. Both tubes have same diameter. Same diameter. And the tubes are in resonance in first overtone. Their first overtone. We have to find end correction. C is what? End correction. We know that closed pipe has only one end correction, whereas open pipe has two end corrections, here and here, C and C. Therefore, according to question, now according to question, its first overtone frequency is equal to its first overtone frequency, means first overtone frequency of means F2 of closed pipe is equal to F2 of open pipe. That is, F2 of closed pipe is 3, F1 of closed pipe is equal to 2 F1 of open. Therefore, 3 F1 of closed pipe means B upon 4 L of closed pipe plus 1 end correction is equal to 2 B upon 2 L of open pipe plus 2 end corrections, 1 here and 1 here. So velocity gets cancelled, and putting the values we get 3 upon 4 LC means 23 plus end correction is equal to 2 upon 2 L open is 30 plus 2 C. On simplification we get C is equal to 1 cm, which is 0.01 meter. Next question number 8. A piano string of length 1.5 meter and density 7,800 kg per meter cube has Young's modulus 2 into 10 to power 11 Newton per meter square. It is maintained at tension which produces a strain of 1% in the string. Find the frequency of vibration of transverse wave when wave in string vibrating in second mode. Solution to question 9. Given for piano string. Piano string means staged string. Density 7,800 kg per meter cube. Length 1.5 meter. Young's modulus 2 into 10 to power 11 Newton per meter square. We have to find F2. Frequency in second mode. strain, longitudinal strain is 1%, means 1 upon 100, which is 0.01. Now F2 is equal to 1 upon 2L under root T upon M, where M is pi r square rho, so it is 1 upon 2L under root T upon pi r square into rho. Suppose this is equation 1. Now Young's modulus Y is equal to stress upon longitudinal strain is equal to stress, means force per unit area, upon strain is 0.01. So this is Y is equal to F upon 0.01 A. Force is equal to tension, therefore it can be written as T upon 0.01 A, because T is equal to A. T is equal to force, tension is equal to force, therefore T can be written as 0.01 YA, equation 2. With equation 2, question 1 gives F2 is equal to 1 upon 2, L is 1.5, 2L under root T is equal to 0.01 Y into A upon pi r square into rho. A cancels pi r square because A is equal to cross section area pi r square. Therefore F2 will be equal to 1 upon 3 into 0.01. Y is 2 into 10 to the power 11 upon rho is 7800. On simplification, we get frequency as 337.58 Hz. Next question number 10. A uniform tube of length 60 cm stands vertically with its lower end dipping in water. When the length above water is 14.8 cm and again at 48 cm, the tube resounds with tuning fork of frequency 512 Hz. Find the lowest frequency with which the tube will resound when it is totally in air. According to question, L is equal to length of open pipe, 60 cm. When it is dipped in water with 14.8 cm in air, then L1 is equal to 14.8 cm. It resounds with, and similarly when it is dipped in water with 48 cm in water, above water, in air, similarly when it is dipped in water with 48 cm in air, then resonates with the tuning fork of frequency 512 Hz. So we have to find F minimum frequency of tube in air. When tube is totally in air, then what will be its minimum frequency? Solution. This is similar to resonance tube experiment. So V will be equal to 2F into L2 minus L1, 2 into 512 into 48 minus 14.6, which gives velocity of sound in air at lab temperature as 33,979 cm per second, which is equal to 339.79 meter per second. Also, end correction C is equal to L2 minus 3L1 upon 2, which is end correction of resonance tube. 48 minus 3 into L1 is 14.8 upon 2, which gives end correction as 1.8 cm, which is 0.018 meter. When the tube is in air, we have minimum frequency F minimum as B upon 2L plus 2C, which is equal to B 339.79 upon 2 taken common. L is 0.6 meter plus end correction C is 0.018, which gives 275.06 Hz. Next question number 11. An open organ pipe is tuned to a frequency of 440 Hz at 27 degree Celsius. Find its frequency at 0 degree Celsius. Solution to question 11. Given for open pipe, F is equal to 440 Hz at temperature T1 is equal to, or T is equal to 300 Kelvin, 27 degrees Celsius. What will be the frequency at 0 degrees Celsius? Means 273 Kelvin. Now we know that for open pipe, V is directly proportional to, or frequency is proportional to B, which is proportional to root of absolute temperature. Therefore, F upon F dash will be equal to, or F, therefore F upon F naught will be equal to T upon T naught. This gives F naught as F T naught upon T means 440 under root 273 upon 300, which gives 419.73. Next question number 12. A steel wire of mass 3 gram and length 2 meter is under tension of 500 Newton and is tied at both ends. Calculate the frequency and wavelength for fundamental mode. So, solution to question 12. Given for staged wire, steel wire, L is 2 meter and mass is 3 gram means 0.003 kilogram. Tension is 500 Newton. First, fundamental frequency. Second, corresponding wavelength means wavelength corresponding to fundamental mode. Now, F1 will be equal to first 1 upon 2L under root T by M, where M is mass per unit length, mass is 0.003 upon length is 2, this is 0.0015 kg per meter. Therefore, F1 will be equal to 1 upon 2 into 2 under root 500 upon 0.0015, which gives a frequency F1 as 144.3 Hertz. Second part, in fundamental mode, lambda 1 will be equal to 2L. Therefore, 2 into 2 is equal to 4 meter. Next question number 13. A steel wire of diameter 0.04 cm and density 8000 kg per meter cube is under a constant tension of 80 Newton. What length of wire should be plugged to cause it to vibrate with frequency 840 Hz? Solution to question 13. Given diameter 0.04 cm means radius 0.02 cm means 10 to minus 2 meter. This is radius of steel wire. Density 8000 kg per meter cube. Constant tension 80 Newton. Length required to vibrate with frequency, if frequency is 840 Hz. Now, F is equal to 1 upon 2L under root T by M, which is 1 upon 2L under root T by pi r square into rho. Therefore, L will be equal to 1 upon 2f, 1 upon 2f under root T upon pi r square into rho. Values are known. 1 upon 2 into 840. T is 80. Pi r is 0.02 into 10 to power minus 2 square into rho. Rho is 8000, which gives required length as 0.168 meter. Next question number 14. A steel wire of length 40 cm and diameter 0.25 millimeter is in unison with an open tube of effective length 60 cm when each is sounding in its fundamental mode at 27 degrees Celsius. Find the tension in wire. Given velocity of sound in air at 0 degrees Celsius is 332 meter per second and density of steel is 800 kg per meter cube. So, solution to question 14. Given L is equal to 40 cm, which is 0.4 meter. This is length of steel wire. Radius of steel wire is 0.25 millimeter, which is diameter, upon 2 0.125 millimeter multiplied by 10 to minus 3 gives meter. Density of steel wire is 7800 kg per meter cube. This is density of steel. Length of open pipe is 60 cm, that is 0.6 meter. This is length of open pipe, open tube. Temperature is 27 degrees Celsius, means 300 Kelvin. At this temperature, the vibrating wire and open tube are in unison. Unison means at resonance. So, in fundamental mode means F1 wire is in unison with F1 open tube. Here, because unison means resonance, that is having same frequency. V0 is equal to 332 meter per second. Velocity of sound in air at 0 degrees Celsius. We have to find the tension in the string. Now, if V is the velocity of sound in air at temperature T, then we know V upon V naught will be equal to under root T upon T naught, which gives V as V naught T upon T naught. V 332, T is 300 and T naught 273. This gives 3 Celsius as 348 meter per second. Now, according to question, in fundamental mode, F1 of string is equal to F1 of string is equal to F1 of open pipe. That is 1 upon 2 L of a string into under root T by M is pi R square into rho will be equal to B upon 2 L open, because fundamental frequency of open organ pipe is B upon 2 L. Here 2 cancels out and squaring both sides we get 1 upon L square the root T upon pi R square into rho is equal to B square upon L naught square. This gives tension T as pi rho R square L square pi rho R square L square B square upon L naught square, or you can write it as pi rho R square L square B square L naught square means R L B upon L naught whole square. Pi rho is 7,800 into radius is 0.125 into 10 to minus 3 into length of wire is 2 meter. So length of wire is 0.4 meter. This one. Velocity 348 upon L naught is open valve as length 0.6 its square. So we get tension in the string as 20.6 Newton. Question number 15 is a piano string of length 2 meter and density 8000 kg per meter cube suffers a strain of 1% due to tension in the tension. Or question number 15, a piano string of length 2 meter and density 8000 kg per meter cube suffers a strain of 1% due to tension in fundamental mode of vibration with frequency 170 Hz. Find Young's modulus of the material of wire. So solution to question 15 given are piano string means stage distance, length is 2 meter, fundamental frequency is 170 hertz. See? Strand, change in length upon original length, that is longitudinal strand. One percent means 1 upon 100 means 0.01. Density 8000 kg per meter cube. We have to find Young's modulus. Of steel. Now we know that fundamental frequency of stretched wire is given by 1 upon 2L under root T by M, which is 1 upon 2L under root T upon pi r square into rho. Suppose this is equation 1. Also, Young's modulus Y is equal to stress upon longitudinal strand. The stress is force per unit area, and longitudinal strain is change in length upon original length. Force is equal to tension, so you can write it as T upon A, and strain is 0.01, because force is equal to T is equal to tension applied. So Y will be equal to T upon 0.01 times A. Suppose this is equation 1. Sorry, or T is equal to T. So Y is equal to T upon 0.01 A, which gives T as 0.01 Y times A, equation 2. This is equation 2. Therefore, with equation 2, equation 1 gives F1 is equal to 1 upon 2L under root T is equal to 0.01 Y into A upon pi r square into density. A can be cancelled with pi r square because A is equal to pi r square. This is cross section of wire. Area of wire. So we get F1 square is equal to 1 upon 4 L square on squaring both sides into 0.01 y upon rho, which gives y as 4 rho f1 square L square upon 0.01. 4 rho is 8000, f1 is 170, L upon 0.01, which gives Young's modulus as 3.699 into 10 to power 11 Newton per meter square, which is nearly 3.7 into 10 to power 11 Newton per meter square.